Hello! Now, today we are going to be introducing the idea of equations and equations involving algebra, but we already know a lot about equations. We've been using them for years. So I'm going to give you an example of how it is we can play around with equations not involving algebra and see if we can get a feel for what's going on and how we're going to do things when we do have algebra involved. So I'm claiming we've used equations for years. Let's look at what I mean. If I have 3 plus 7, that is equal to 10. Everyone's happy that that's true. But what have we got? We've got an equal sign. There's an equal sign in between these two things. Now what does that mean? It means that they are the same as each other. So 3 plus 7 is the same as 10. If we have 3 of something and 7 of something, in total we have 10 of it. So 3 plus 7 is the same as, is equal to 10. Now all throughout our time in maths, equal sign is always going to mean the same thing. We're going to use it in lots of complicated ways, but it's always going to mean the same thing, and if we can hold on to that fact, it's going to help us. Now, the next few things I'm going to do aren't really for any justifiable reason other than to show you how it is we can change the way a sum looks without breaking the meaning of the equal sign, that the stuff on the left hand side is going to be equal to or the same as the stuff on the right hand side. That's my real aim at the beginning. So we're all happy that 3 plus 7 is equal to 10. But what would happen if I decided I wanted to take 2 away from this? I want to take away 2 from this left hand side. Well, what does the problem become? It becomes 3 plus 7 minus 2. But that isn't equal to 10 anymore. 3 plus 7 minus 2, if we did out the sum, would equal 8. So what happened? What happened was we would have to take away 2 from the 10 as well in order to keep things balanced, in order to keep our equation. So to keep an equal sign in between the left and the right hand side, I have to take away 2 from the right as well. So let's do this out. We'd have 3 plus 7 is 10 minus 2 is 8 is equal to 10 minus 2 is 8. So when I say that the equal sign is preserved, or I mean that the equal sign is kept, it means that the left hand side is still equal to the right hand side. This number is still the same as this number. So we can see that we are able to take away something from both sides of our equation, from the left hand side and from the right hand side, and the equality doesn't break. 8 is still equal to 8. Likewise, if I started at this position, I could add, say, 10 to both sides. So if I add 10 to this left hand side, I want to have 18. So I add 10. Well, 18 is not equal to 8. What do I have to do in order to make the left hand side equal to the right hand side? I have to add 10 to the opposite side as well, and now I have 18 equals 18, and that's true. I'm going to take another example now. If I had multiply, so if I have 8 multiplied by 2 is equal to 16. That's true. If I multiply 8 by 2, I get 16. We're all happy that that's true. But say I just want to know that 8 was equal to 8. Again, there's very little reason why we'd be bothering to do this in the circumstances I'm showing you right now, but it turns out that this is very useful when we want to rearrange equations, when we want to deal with equations that involve algebra. So if I have 8 multiplied by 2 is equal to 16, it would still be true that if I divided this by 2 and this by 2, I would still get an equality. I would still get the left-hand side equal to the right-hand side because I have divided both sides by the same amount. Well, what would the numbers work out to? I'd have 2 divided by 2, so 2 divided by 2. I'd divide out that common factor top and bottom, and I'd be left with 8 on the left-hand side. Now if I have 16 divided by 2, I know 16 divided by 2 is 8. So I could divide both sides by 2, and if I did it to both sides, if I divided both sides by the same number, I'd keep my equality. 8 is still equal to 8. So I can see that I'm able to multiply and divide, add and subtract by the same amount to both sides of my equation, and I keep the equality. I don't break the fact that the left-hand side is equal to the right-hand side. Well, let's take some algebra now and see if we're able to do the same type of thing. So we have these steps here available to us. Let's try the same type of thing. If I have A is a letter, and I don't know what A is yet, plus 3 is equal to 19. And I want to know what A is. Now I can work out what A is in my head in this particular case, but we can practice methods that are going to help us in harder problems. So, I want to end up with, in this case, and in all algebra, I'm going to have an aim in mind. I want to have my letter is equal to a number. I want to have 1A is equal to a number. And I don't know what the number is yet. That's what I'm trying to find out. But I want to know what 1 of A is. And at the moment I know that A plus 3 is equal to 19. Well, without doing stuff in my head, using the structures that I've practiced here, I'm going to figure out how to get 1A is equal to a number, which is my aim. What I'm going to do is subtract 3 from this side. Now, why do I want to do that? Because I want to end up with A is equal to a number. And at the moment, I have A plus 3 is equal to a number. And I don't want this 3 here. I want 0 numbers on the left-hand side. I just want to have an A on the left-hand side. But I've run into a problem now because this equality is broken. I've taken away 3 from my left-hand side, but I haven't changed my right. So to keep my equality, I'm going to need to take away 3 from the right-hand side, just like I did with my example here, where I had to take 2 from both sides of my equation to keep my equal sign true. So when I do that, I have A plus 3 minus 3 adds up to 0 as we wanted, because we didn't want A to be with anything on the left-hand side. Then my equal sign. And then I have 19 minus 3 is 16. So A is the number 16. Now that's what I wanted to know. 1A, A by itself means 1A, is equal to 16. Let's try another one. C minus 10 is equal to 23. Now my aim is to end up with 1C is equal to number. I don't know what the number is yet. How am I going to get C by itself? I want to end up with 1 of C is equal to number. What I can do is get this side to have the numbers add up to 0. So at the moment I have C minus 10 and I want C plus 0 effectively. I want C by itself. So what I can do is add 10 to my left hand side, because minus 10 plus 10 is 0, and I'll just be left with C on the left hand side. So I'm happy. I have C by itself on the left hand side because I added 10, and that gets rid of my minus 10 there. because it adds up to 0. Minus 10 plus 10 is 0, and I'm just left with c. But to keep everything balanced, I have to write plus 10 on the right-hand side, because I have to change both sides by the same amount, just like I saw here. If I only added 10 to my left-hand side, I've had 18 equals 8, which isn't true. So I have to add 10 to both sides of my equation. So when I do that, I have 23 plus 10 is equal to 33. And now I have what I wanted. I have 1c is equal to number. And that's what I like. Now, one thing I wanted to mention is that we often want to verify, and verify is just a fancy word for check, verify, or check our answers. It's very important to get into the habit of doing this. So if I wanted to verify my answer, all I do is take my original equation, c minus 10 is equal to 23, and then I take the fact that I know that c is equal to 33 and see if the equation works out. So c is equal to 33, just like our older problems in algebra. We're going to put a 33 anywhere there was a c. We always sub in brackets. Equal to 23. Now there's nothing multiplying this bracket, so I just have 33 minus 10 is 23 is equal to 23. And that's true. 23 is equal to 23. So my equation works out. Now, if I had something like 2x is equal to 30. If I had something like 2x is equal to 30, I want to end up with 1x is equal to a number. I have 2x is equal to 30. Well, what would I do in that situation? I want to have 1x here, so I'm going to divide by 2. And to keep everything balanced, I have to do the same on the other side. So if I have 2 divided by 2, I get 1x is equal to 30 divided by 2 is 15. And I've got what I wanted. I have 1x is equal to 15. And this is going to be a pattern that we'll often see. If we have 2 or any number multiplied by x, if we divide by that number, any number divided by itself will leave me with 1. And I always want to end up with 1x or 1a or so on. So again, if I had 10x is equal to 200, how would I get 1x is equal to? I would divide both sides by 10. 10 divided by 10 will leave me with 1x on the left hand side, which is what I want, is equal to, I have to change the right hand side by the same amount, so I have to divide by 10, and I end up with 20. And again, we can verify or check our answers. Finally, for now, we could have x divided by 5 would be equal to 3. And I want to know what x is by itself. Well, I know again, any number divided by itself is going to be 1. So to get 1x is equal to a number, I would multiply both sides by 5. I would multiply by 5 here because 5 divided by 5 is 1. So I'll be left with my 1x on the left hand side, and then I'd multiply by 5 on the right hand side, and that is going to give me 15. Now, a tool that can be useful for remembering that we have to keep our balance is to imagine that the left hand side of our equal sign is on a weighing scales on the left, and or on the scales on the left, and the right hand side of our equation is on a weighing scales on the right. And if we take away the same amount from both sides, we keep our equation balanced. And that's another useful way to think about equations.